Good morning, good evening, जिथे जो है greeting accept करियो. Page number 217. Next topic is mass, matter and reality. Let us briefly take stock of the picture of the world that classical physics has presented us with. First, there is space-time playing a primary role as the arena for all the varied activity of physics. Second, there are physical objects indulging in this activity but constrained by precise mathematical laws. The physical objects are of two kinds, particles and fields. One of the particles, little is said about their actual nature and distinguishing qualities, save that each has its own word line and possesses an individual rest mass and perhaps electric charge, etc. The fields, on the other hand, are given very specifically, the electromagnetic field being subject to Maxwell equations and the gravitational field to the Einstein equations. There is some ambivalence about how the particles are to be treated. If the particles have such tiny mass that their own influence on the fields can be neglected, then the particles are called test particles, and then their motion in response to the fields is unambiguous. The Lorentz force law describes the response of test particles to the electromagnetic field, and the geodesic law their response to the gravitational field in an appropriate combination when both fields are present. For this, the particles must be considered as point particles, that is, having one-dimensional word lines. However, when the effects of the particles on the fields need to be considered, that is, the particles act as source for the fields, then the particles must be considered as objects spread out to some extent in space. Otherwise, the fields in the immediate neighborhood of each particle become infinite. These spread out sources provide the charge current distribution that is needed for Maxwell's equations and the tensor energy that is needed for the Einstein's equations. In addition to all this, the space-time in which all these particles and fields reside has a variable structure which itself directly describes gravity. The arena joins in the very action taking place within itself. This is what classical physics has taught us about the nature of physical reality. It is clear that a great deal has been learned, and also we should not be too complacent about that the pictures that we have formed at any one time are not to be overturned by some later and deeper view. We shall see in the next chapter that even the revolutionary changes that relativity theory has wrought will pale almost to insignificance in comparison with those of the quantum theory. However, we are not quite finished with the classical theory and with what it has to say to us about material reality. It has one further surprise for us. What is matter? It is the real substance of which actual physical objects, the things of this world, are composed. It is what you, I, and our houses are made of. How does one quantify this substance? Our elementary physics textbooks provide us with Newton's clear answer. It is the mass of an object or of a system of objects which measures the quantity of matter that it contains. This indeed seems right. There is no other physical quantity that can seriously compete with mass as the true measure of total substance. Moreover, it is conserved. The mass and therefore the total matter content of any system, whatever, must always remain the same. Yet Einstein's famous formula from special relativity E is equal to mc squared tells us that mass and energy are interchangeable into one another. For example, when a uranium atom decays, splitting up into smaller pieces, the total mass of each of these pieces, if they could be brought to rest, would be less than the original mass of uranium atom. But if the energy of motion, kinetic energy, of each piece is taken into account and then converted to mass values by dividing c square, then we find that the total is actually unchanged. Mass is indeed conserved, but being partly composed of energy, it now seems less clearly to be the measure of actual substance. Energy, after all, depends upon the speed with which what substance is traveling. The energy of motion in an express train is considerable, but if we happen to be sitting in that train, then according to our viewpoint, the train possesses no motion at all. The energy of that motion, though not the heat energy of the random motions of individual particles, has been reduced to zero by this suitable choice of viewpoint. For a striking example where the effect of Einstein's mass energy relation is at its most extreme, consider the decay of a certain type of subatomic particle called pi naught or pi zero meson. It is certainly a material particle having a well-defined positive mass. After some 10 raised to power minus 16 of a second, it disintegrates like the uranium atom above, but very much more rapidly, almost always into just 2 photons. For an observer at rest with the pi zero meson, each photon carries away half the energy and indeed half of the pi zero meson's mass. Yet this photon mass is of a nebulous kind, pure energy, for if we were to travel rapidly in the direction of one of the photons, then we could reduce its mass energy to as small a value as we please, the intrinsic mass of a photon being actually zero. All this makes for a consistent picture of conserved mass, but it is not quite the one we had before. Mass can still, in a sense, measure quantity of matter, but there has been a distinct change of a viewpoint. Since mass is equivalent to energy, the mass of a system depends, like energy, upon the motion of the observer. So they have a momentum going in, they have a picture, the energy momentum forward vector. So they have a time axis, they have a momentum, and they have a Minkowski cone, and there is an energy moment forward vector which is kind of a diagonal to the square of momentum and time axis, and the energy is basically this. Okay, it is worthwhile to be somewhat more explicit about the viewpoint that we have been led to. The conserved quantity that takes over the role of mass is an entire object called the energy momentum forward vector. This may be pictured as an arrow at the origin in Minkowski space pointing inside the future light cone at or in the extreme case of a photon on this cone. This arrow, which points in the same direction as the object's word line, contains all the information about its energy, mass, and momentum. This t value or height of the tip of this arrow is measured in some observer's frame, describe the mass of the object according to that observer, while the spatial components provide the momentum. The Minkowskian length of this arrow is an important quantity known as the rest mass. It describes the mass for an observer at rest with the object. One might try to take the view at that this would be a good measure of quantity of matter. However, it is not additive. If a system splits into two, then the original rest mass is not the sum of the resulting two rest masses. Recall the pi zero meson decay considered above. The pi zero meson has a positive rest mass, while the rest masses of each of the two resulting photons is zero. However, this additivity property does indeed hold for the whole arrow. We must now add in the sense of the vector addition law depicted in figure 5.6. It is now the entire arrow which is our measure of quantity of matter. Think now of Maxwell's electromagnetic field. We have noted it carries energy by E is equal to mc squared. It must also have mass. Thus, Maxwell's field is also matter. This must now certainly be accepted since Maxwell's field is intimately involved in the forces which bind particles together. There must be a substantial contribution to anybody's mass from the electromagnetic fields within it. What about Einstein's gravitational field? In many ways, it resembles Maxwell's field, similarly to the way that with Maxwell's theory, charged bodies in motion can emit electromagnetic waves. Massive bodies in motion can emit gravitational waves, which, like electromagnetic waves, travel with the speed of light and carry energy. Yet this energy is not measured in the standard way, which would be by the tensor energy referred to the before. In a pure gravitational wave, this tensor is actually zero everywhere. One might take the view, nevertheless, that somehow the curvature of space-time, now given entirely by the tensor veil, can represent the stuff of gravitational waves, but the gravitational energy turns out to be non-local, which is to say that one cannot determine what the measure of this energy is by merely examining the curvature of space-time in limited regions. The energy and therefore the mass of a gravitational field is a slippery eel indeed and refuses to be pinned down in any clear location. Nevertheless, it must be taken seriously. It is certainly there and has to be taken into account in order that the concept of mass can be conserved overall. There is a good measure of mass which applies to gravitational waves, but the known locality is such that it turns out that this measure can sometimes be non-zero in flat regions of space-time between two bursts of radiation, where the space-time is actually completely free of curvature. That is, both Weyl and Ricci are zero. In such cases, we seem to be driven to deduce that if this mass energy is to be located at all, it must be in this flat empty space, a region completely free of matter or fields of any kind. In these curious circumstances, our quantity of matter is now either there in the emptiest of empty regions or it is nowhere at all. This seems to be pure paradox, yet it is definite implication of what our best classical theories, and they are indeed superb theories, are telling us about the nature of the real material of our world. Material reality, according to classical theory, let alone in the quantum theory that we are about to explore, is a much more nebulous thing than one had thought. Its quantification, and even whether it is there or not, depends upon distinctly subtle issues and cannot be ascertained merely locally. If such non-locality seems puzzling, be prepared for much greater shocks to come. It is, I think that finishes up chapter 5. That was fast. Chapter 6 is Quantum Magic and Quantum Mystery. Do philosophers need quantum theory? In classical physics, There is, in accordance with common sense, an objective word out there. The word evolves in a clear and deterministic way, being governed by precisely formulated mathematical equations. This is as true for the theories of Maxwell and Einstein's as it is for the original Newtonian scheme. Physical reality is taken to exist independently of ourselves, and exactly how the classical world is not affected by how we might choose to look at it. Moreover, our bodies and our brains are themselves to be a part of that world. They also are viewed as evolving according to the same precise and deterministic classical equations. All our actions are to be fixed by these equations, no matter how we might feel that our conscious wills may be influencing how we behave. Such a picture appears to lie at the background of most serious philosophical arguments concerned with the nature of reality, of our conscious perceptions, and of our apparent free will. Some people might have an uncomfortable feeling that there should also be a role for quantum theory, that fundamental but disturbing scheme of things which in the first quarter of the century arose out of observations of subtle differences between the actual behavior of the world and the descriptions of classical physics. To many, the term quantum theory, evokes merely some vague concept of an uncertainty principle, which at the level of the particles, atoms, or molecules forbids precision in our description and yields merely probabilistic behavior. Actually, quantum descriptions are very precise, as we shall see, although radically different from the familiar classical ones. Moreover, we shall find, despite a common view to the contrary, that probabilities do not arise at the minute quantum level of particles, atoms, or molecules. Those evolve deterministically, but seemingly via some mysterious larger scale action connected with the emergence of a classical world that we can consciously perceive. We must try to understand this and how quantum theory forces us to change our view of physical reality. One tends to think of the discrepancies between quantum and classical theory as being very tiny, but in fact, they also underlie many ordinary scale physical phenomena. The very existence of solid bodies, the strengths and physical properties of materials, the nature of chemistry, the colors of substances, the phenomena of freezing and boiling, the reliability of inheritance, these and many other familiar properties require the quantum theory for their explanations. Perhaps also the phenomena of consciousness is something that cannot be understood in entirely classical terms. Perhaps our minds are qualities rooted in some strange and wonderful feature of those physical laws which actually govern the world we inhabit, rather than being just features of some algorithm acted out by the so-called objects of a classical physical structure. Perhaps in some sense this is why we as sentient beings must live in a quantum world rather than an entirely classical one, despite all the richness and indeed mystery that is already present in the classical universe. Might a quantum world be required so that a thinking, perceiving creatures such as ourselves can be constructed from its substance? Such a question seems appropriate more for a god intent on building an inhabited universe than it is for us. But the question has relevance for us also. If a classical world is not something that consciousness could be part of, then our minds must be in some way dependent upon specific deviations from the classical physics. This is a consideration I shall return to later in this book. We must indeed come to terms with quantum theory, that most exact and mysterious of physical theories. If we are to delve deeply into some major questions of philosophy, how does our world behave, and what constitutes the minds that are indeed us? Yet someday science may give us a more profound understanding of nature than quantum theory can provide. It is my personal view that even quantum theory is a stopgap, inadequate in certain essentials for providing a complete picture of the world in which we actually live, but that gives us no excuse. If we are to gain something of a philosophical insights we desire, we must comprehend the picture of the world according to existing quantum theory. Unfortunately, different theorists tend to have very different viewpoints about the actuality of this picture. Many physicists, taking their lead from the central figure of Niels Bohr, would say that there is no objective picture at all. Nothing is actually out there at the quantum level. Somehow, reality emerges only in relation to the results of measurements. Quantum theory, according to this view, provides merely a calculational procedure and does not attempt to describe the world as it actually is. This attitude to the theory seems to me to be too defeatist, and I shall follow the more positive line which attributes objective physical reality to the quantum description, the quantum state. There is a precise equation, the Schrödinger equation, which provides a completely deterministic time evolution for this state. But there is something very odd about the relation between the time evolved quantum state and the actual behavior of the physical world that is observed to take place. From time to time, whenever we consider that a measurement has occurred, we must discard the quantum state that we have been laboriously evolving and use it only to compute various probabilities that the state will jump to one or another of a set of new possible states. In addition to the strangeness of this quantum jumping, there is the problem of deciding what is about a physical arrangement that decrees that a measurement has actually been made. The measuring apparatus itself is, after all, presumably built from quantum constituents and so should also evolve according to the deterministic Schrödinger equation. Is the presence of a conscious being necessary for a measurement actually to take place? I think that only a small minority of quantum physicists would affirm such a view. Presumably, human observers are themselves also built from minute quantum constituents. Later in this chapter, we shall be examining some of the strange consequences of this jumping of the quantum state. For example, how a measurement in one place can seemingly cause a jump to occur in a distant region. Earlier on, we shall encounter another strange phenomenon, sometimes two alternative routes that an object can take perfectly well if either is traversed separately will cancel one another out completely as soon as both are allowed together. So now neither can be traversed. We shall also be examining in some detail how quantum states are actually described. We shall see how greatly these descriptions differ from the corresponding classical ones. For example, particles can appear to be in two places at once. We shall also begin to get some feeling for how complicated are quantum descriptions when there are several particles to be considered together. It turns out that the particles do not each have individual descriptions but must be considered as complicated superpositions of alternative arrangements of all of them together. We shall see how it is that different particles of same type cannot have separate identities from one another. We shall examine in detail the strange and fundamentally quantum mechanical property of spin. We shall consider the important issues raised by the paradoxical thought experiment of Schrodinger's cat, and of various different attitudes that theorists have expressed, partly as attempts to resolve this very basic puzzle. Some of the material in this chapter may not be quite so readily comprehended as that of the preceding chapters and is sometimes a bit technical. In my descriptions, I have tried not to cheat, and we shall have to work a little harder than otherwise. This is so that we can attain some genuine understanding of the quantum world. Where an argument remains unclear, I advise you that you press on and try to gain a flavor for the structure as a whole, but do not despair if a full understanding proves elusive. It is in the nature of the subject itself. Problems with classical theory. This one will be a short video. Let's continue in the next.